We are 266,000 times farther away from Proxima Centauri than we are from the Sun, and we have traveled 103 million times farther than we did to conquer the Moon. Proxima Centauri is the nearest star to Earth. Amazing, isn't it? Even a light ray traveling at the fastest possible speed is 4.3 years away from Earth from Proxima, although it only takes less than 8.5 minutes to travel the distance between us and the Sun. The issue of interplanetary travel is included in these figures and their unrelenting inevitableness. When we contemplate the vastness of our galaxy, approximately 100.000 light-years in diameter, and the size of the observable universe, more than 12 billion light-years, we cannot help but feel profoundly inadequate when we face the question of the journeys in the cosmos. When we consider that the Voyager 1 probe, the fastest interstellar object ever created by man, is traveling away from the Sun at a speed of 17 kilometers per second and will take around 75,000 years to reach Proxima, we can see how limited our current technical capabilities are. It is obvious that ordinary chemical fuel rockets are completely insufficient for such distances and that a significant technological advance is required, even with the gravity assist of Jupiter and Saturn. Numerous solutions have been put forth in this area, ranging from giant sails propelled by light to rockets driven by matter-antimatter annihilation and nuclear fission and fusion. These are simply theoretical solutions that would necessitate years of research and development as well as significant financial and technological investments. There are many who have suggested using wormholes or warp engines in the far future, and everything needs to be verified, which are fantastical solutions based on the general relativity hypothesis taken to its logical conclusion that could guarantee motions faster than the speed of light. But regrettably, the solution does not lie in developing larger, better, and faster spacecraft or in just waiting for science and technology to advance naturally. Our intentions for free and quick navigation in the galaxy are slowed down, if not prevented, as we will discover in a moment, by an impossible imposed by physics. It would be necessary to greatly raise the pace for interplanetary travel to become appealing to humans and to elicit the concoction of aspiration, ambition, curiosity, and competition that drives our greatest undertakings. But for a number of reasons, this is completely impossible. The implied findings of the well-known Fermi paradox also serve to illustrate this impossibility. Then, follow me, and if I'm mistaken, please correct me. Rolling intro: no object with mass is capable of traveling faster than the speed of light, as Albert Einstein initially stated in his special theory of relativity in 1905. This does not change the fact that the limit has been proven in numerous experiments, and that regarding matter and the universe we know there is no longer the slightest reason to doubt its existence. Einstein established this limit based on considerations that seemed, and still seem, to conflict with the common sense with which we are accustomed to evaluate the physical phenomena of our daily life. In fact, Einstein proved that any object's energy, or E, and mass, or m, are related by the famous equation E equals mc squared, where c denotes the speed of light, or 299.792 for 58 kilometers per second in a vacuum. This equation implies, among other things, that mass and energy are two equal and interchangeable entities. And even if we are unaware of it, this is exactly what happens when we accelerate an object. A very little portion of the energy we give it is used to increase its mass. However, when the speed rises, we need more and more energy to keep the speed up, which occurs because more and more energy is converted into mass. In reality, an item becomes increasingly substantial and unyielding as it approaches the speed of light. For instance, if it moved at 99.9% the speed of light, an 80 kilograms person would weigh nearly 2 tons. Therefore, trying to raise the object's or spaceship's push in order to get it past the barrier of 300.000 kilometers per second would simply have increased the mass exponentially while essentially maintaining the speed. Because of this, speed c can only ever be approached. In other words, bodies with mass resist being accelerated to speeds that are close to the speed of light, and the closer you go to this speed, the harder it is to accelerate them further. And even if you could instantly travel at the speed of light using a miracle device, it would still take 4.3 years to reach Proxima Centauri. This means that even if we traveled at the fastest speed possible in our universe, we would only be able to conduct a few exploration trips around the sun and could not, under any circumstances, build a network of commerce routes spanning the full range of the galaxy. You must have a deep curiosity about human spaceflight and the secrets of the cosmos if you are here watching this video. So subscribe right away and make sure to turn on the bell notification so you never miss out on the latest information about the cosmos. We continually work to create videos that delight an inquisitive person like you. But let's not give up so easily. We might be overlooking something. Yes, since other factors also change with speed besides mass. Time dilation is in fact another aspect of space travel at relativistic speeds to take into account. Contrary to what conventional physics predicts, time does not move at the same rate for all witnesses. Rather, it moves faster as an observer gets closer to the speed of light. The fact that time always moves more slowly inside a spacecraft that departs the Earth while accelerating up to relativistic speeds, regardless of the scientific or mathematical justifications, must be accepted without question. Consider a spacecraft that is going to a planet 9.5 light-years away at 95% the speed of light. The journey's duration would be calculated for a stationary observer on Earth as distance divided by speed, or 9.5 divided by 0.95 is equal to 10 years. On the other hand, the crew members of the spaceship experienced time dilation and believe that the journey took only 3.12 years. In other words, the crew members age slightly more than 3 years between leaving Earth and arriving at their destination, whereas 10 years have passed for those back on Earth. And this time lag is derived from a relatively straightforward formula, which can also predict, for instance, that for a crew aboard a spacecraft traveling at 50% of c, time will appear to pass 1.15 times slower than it does on Earth, while at 75% of c, it will appear to pass 1.5 times slower. Time will move 7 times more slowly on board if the speed hits 99% of c, and so forth. Time will move 70 times slower at 99.99% of c, at 99.9999999% of c. Time will move 22,300 times slower inside the spacecraft. At 100% of c, time will appear to stop completely. These calculations, while in some ways might inspire hope regarding the likelihood of being able to move around the galaxy at pleasure, reveal something shocking. They claim that in reality, a traveler in a spacecraft flying at a speed of almost 100% of the speed of light will reach any location, whether it is 100 light years or 100,000 light years distant, in practically an instant. You don't think so? So let's look at a compelling example. The Andromeda Galaxy, located roughly 2.5 million light-years away from Earth, is where we wish to travel. The journey would undoubtedly take for roughly 2.5 million years if it were carried out with acceleration capable of accelerating the ship to a speed equivalent to 99.99% of c, yet on board the ship, the apparent time would only be 35,000 years. In addition to that, in just 30 kilometers per second more, the speed would increase to 99.999999999% of the speed of light, and Andromeda would be within approach in little over 11 years. Isn't that amazing? If it were truly possible, we could be able to realize the much-touted Star Trek scenario where spaceships easily move from one galaxy to the next. Does time dilation therefore resolve the issue? Well, regrettably, no. As we have already learned, it would take almost unlimited energy to accelerate a mass to the point where it would touch the speed of light. We could not get this contribution from any known kind of propulsion at this time. A spacecraft flying at a speed extremely close to the speed of light would put itself in a particularly dangerous situation, even if the energy problem were to be resolved in some manner by means that we are utterly unable to predict. In actuality, space is not void. Contrarily, it is teeming with stray atoms, some of which combine to form more complex structures like the gas and dust of interstellar clouds, galaxies, stars, and planets, while others remain lone atoms traveling in a vacuum and likely won't collide with another atom for countless thousands of years. The likelihood of a collision between two hydrogen atoms in a cubic centimeter of space is one thing, but the likelihood of the massive stream of particles colliding with the spaceship during its journey is another. When traveling at low speeds, particles are practically harmless, but when they accelerate, they become a deadly shower of projectiles and ionizing radiation with tremendous penetrating strength, capable of causing major hull damage and rendering the interior dangerously radioactive for the occupants. When the particles are intercepted at speeds close to the speed of light, they gain enough energy to be fatal to any type of life on board. Not to mention that at that speed, it could be possible to cause the ship's total destruction by piercing a thin nebular veil. Some researchers believe that interstellar matter alone will be enough to prohibit a spacecraft from traveling faster than 1/10 the speed of light. However, as we have shown, this is far from enough to support a network of extensive trade and exploration routes. Even if all of these challenges were resolved, there would still be one problem that was utterly insurmountable. Time dilation would really destroy all connections between the traveling starship and the planet of origin. The astronauts would leave with the knowledge that they would never see their families, friends, or relatives again unless they brought them with them or did not have any at all. On the other hand, when they returned, they would find a society that was significantly different from the one they had left. Not only that, but such a method of travel could not permit the existence of interstellar organizations like the United Federation of Planets, which rely solely on trade and cultural exchanges between various races and assume a homogeneous level of technological and social progress, homogeneity that is incompatible with the amount of time needed for interstellar travel as currently conceived. Considering that a future commercial firm will never see or speak with the spaceship carrying its cargo, what might possibly motivate it to send its wares to the opposite side of the galaxy? In reality, every starship that enters the domain of Einsteinian relativity will become into a world unto itself, devoid of a home and a past. What would the purpose of that be? In actuality, this is a hypothetical situation that will never come to pass. Enrico Fermi informs us of this using the reasoning behind his well-known conundrum. If extraterrestrials are genuine, the Italian physicist reasoned, why aren't they already here? A simple thought can provide the answer to the following query. According to what occurred to our species, the universe as we know it has been around for roughly 13 billion years, and it takes 5 billion for a planet around a solar-type star to support sentient life. This indicates that countless civilizations existed before our own and had eons to create the technology necessary for space travel. Their absence shows that it is impossible for any civilization to travel at the speed of light between stars, and as a result, the correct response to Fermi's question is that their absence does not rule out the possibility of extraterrestrial life. Rather, it just means that neither physics nor space travel offer any means of canceling distances. Absolutely nothing like all the other inhabitants of the galaxy, we will be compelled to live our entire lives in the house's garden and be content with a few arduous explorations of the 2 or 3 nearest stars. The end of that. Thank you for watching, and please like and subscribe.